All right, welcome everyone in YouTube land. So we're going through the equilibrium section of the chapter, and we had been talking about these reactions which were reversible. Reactants turning into products and products turning back into the original reactants, a two-way street that eventually reached that dynamic state of equilibrium, where a chemical is being used up in one reaction as quickly as it's being reproduced in another reaction. So once we get to this point of equilibrium, the concentration of chemicals no longer changes because it's used up as quickly as it's being reproduced. And so we can read our equation from left to right for the forward reaction, just like we'd read an energy diagram from left to right for the forward reaction energy. But we can also read that equation from right to left. And we can also read an energy diagram from right to left for the back reaction. So as we look at our energy diagram here, we've got the energy of the initial reactants, we've got this energy barrier and the energy of activation associated with breaking the bonds to make products. We see our product energy down here at the bottom. The products are lower in energy than the reactants. And so the forward reaction as we see it is a reaction which gives out energy. It's an exothermic reaction. But if we read this same diagram from right to left, as we have down below on the bottom half of the page, interpreting it as a back reaction, now it's our initial reactants which are lower in energy, and our final products are higher in energy. And we've got this much bigger energy involved, this energy of activation involved in breaking the original bonds. More energy going in to break the bonds and considerably less energy coming back out to make the new chemical bonds. And so the back reaction in this case is a endothermic reaction. And we always see this set up with a reversible system. One of the reactions is putting more energy in, like the back reaction in this case. One of the reactions is endothermic, and one of the reactions, as we read the energy diagram in the opposite direction, one of the energy reactions is giving out more energy and is therefore exothermic. This is critical for understanding how changes in temperature affect the position of equilibrium. If we look at an example here with the Haber process for combining nitrogen and hydrogen to produce ammonia, NH3, that forward reaction is the exothermic reaction again because it gives heat energy out. We can recognize the exothermic reaction because that heat term, or as we sometimes have an actual energy value, that energy in kilojoules or calories, the energy value looks like a product coming out of the reaction. So we start with these chemicals, we finish with these chemicals and the energy. So from left to right, energy is coming out. The forward reaction is exothermic. And let's make a note of that. So left to right is exothermic because that heat energy is coming out. We can see that from the diagram. If we start with this much energy compared to where we started, there's this much more energy coming back out by the end. However, as we read the diagram in reverse from right to left, we start with the ammonia and that heat energy. And we put that heat energy in as we drive the back reaction, using up ammonia and that heat to produce nitrogen and hydrogen gas, a decomposition reaction basically. So that back reaction is putting energy in. The back reaction is an endothermic reaction. So this is crucial. Make sure you understand how to interpret the equation in terms of where that energy term is. If the energy looks like one of the products at the end of the equation, then that's the exothermic process. If the energy looks like one of the starting materials, that's energy going in for the endothermic reaction. So how does changes in temperature affect the system? Well, remember we said that the exothermic gives out energy. And the system could use that energy if the temperature decreased. So decreasing temperature means that the reaction has lost energy. And remember, the job of the system is to compensate for any disturbance, compensate for any change. So when temperatures dropped, when we lose that energy, we favor the reaction which will replace the energy lost. And a reaction which replaces energy, the reaction which produces energy, is the exothermic reaction. So decreasing temperature is like removing energy, a little bit like removing a chemical, as we talked about on Monday. And so we've got to replace that chemical. In this case, replace that energy. And the exothermic reaction, which is producing energy, replaces the energy. Apologies for my horrible handwriting as ever. So we drop temperature, we're losing energy, and an exothermic reaction produces energy. So this is how the system compensates when temperature drops. We favor the exothermic reaction. So for example here, the reaction from left to right is the reaction which is producing energy, giving energy out. So if the exothermic reaction is favored, we compensate for that drop in temperature. You can also think about it as a chemical being removed, or in this case, the energy itself being removed. We had said with removing a chemical, equilibrium moves towards that chemical to replace it. And you can use the same analogy for the heat energy. We drop temperature, we lose energy, we move towards the energy term. That's still a movement from left to right. And that is the pathway for the exothermic reaction. So decreases in temperature favor the exothermic reaction. We can follow the exothermic reaction because exothermic reactions give out energy. Now, we can also increase temperature. Let me just clear my screen out a bit here. We can increase temperature. And if we increase temperature, then the reaction has too much energy. Like switching on the hot plate and raising the temperature, we're raising the energy. And again, the system has to compensate for having too much now. And so the way to compensate for having too much energy is to use that energy up. The reaction which uses up energy is the endothermic reaction. Endothermic reactions use up more energy than they produce when new bonds are made. So again, it's a system compensating for that change being forced on it, the increase in temperature. You increase temperature, we have too much energy. You increase temperature, you favor the endothermic reaction. That's our mantra. Drop temperature, we favor the exothermic. Increase temperature, we favor the endothermic. And so as we look for the endothermic reaction, that's a reaction which consumes that heat energy. It's the back reaction in this case. So that rise in temperature would force equilibrium from right to left. Again, you can think about it in terms of the adding a chemical analogy. We had said when we add a chemical, you move away from that chemical's position in the equation. You can use it for an analogy about heat. So if we add too much heat by raising the temperature, we move away from the heat, from right to left in this case, using up that heat energy as we drive the back reaction, the reaction which is endothermic. Any questions about that one? That's probably one of the trickiest pieces of the chapter, along with pressure, which we might look at today, although we'll probably just leave it to Friday. Remember your mind, well, two parts here really. First part is make sure you can interpret your equation and understand which reaction is exothermic and which reaction is endothermic, because we'll always see both. The exothermic reaction is following the reaction so that the heat is coming out at the end. The endothermic reaction, we start on the side with the heat term and move away from it. That's the endothermic process. And then when we think about these changes in temperature, a rise in temperature gives the reaction too much heat, so we have to use it up. The system is compensating. We raise the temperature, we favor the endothermic reaction. We drop temperature, the chemicals no longer have enough energy. We have to compensate for not having enough energy by favoring the reaction which will produce more. That's the exothermic reaction. A drop in temperature favors the exothermic. Okay, we're doing all right. Let's look at some examples. That always helps, of course. Remember, the practice tests for Chapter 6 are up and available. And if people take those practice tests before the exam, you can talk to me about them. Talk to me about the questions you get wrong. And next Monday afternoon, when we come in for lab number 10, would be a perfect time. Actually, next Monday will be the lab on energy and equilibrium. So let's take a look at some examples. So we've got a reaction, nitrogen combining with oxygen to produce the nitric oxide. And so we're asked, what happens if we increase temperature? Remember, a temperature increase is producing or is providing too much energy. We've got too much energy when temperature rises, and we have to compensate and use that energy up. The reaction which uses up energy is the endothermic. More energy goes into an endothermic. So as we look at the equation, we're looking for that energy term, there it is, 43,000 calories of energy. And to consume that energy, we move from left to right. We don't see any energy at the end if we're moving to the right, because it was consumed along with the nitrogen and oxygen. So the forward reaction is the endothermic, and a rise in temperature favors the endothermic, so equilibrium will move to the right. All right, so I was just asking about my headphones there. Luckily, it gives me a little beep to tell me that my headphones switched off. So everybody hear me okay?
Yeah.
Okay. Yeah, it's weird it decides to switch itself off like that. So the temperature rise favors the endothermic, and we can see that the forward reaction is consuming energy. The forward reaction is endothermic. Next one, we're now going to decrease temperature. We have to figure out how the system compensates for that decrease in temperature. Remember, a decrease in temperature is energy lost. And so if we've lost energy, we need a way of replacing it. And we can replace it by favoring the reaction that produces energy. That's the exothermic reaction. So we look for that energy term, there it is there, and we look for the energy term to be something coming out of the reaction. So as we read the equation from left to right, we put in the N2H4, the hydrogen and the oxygen, and we produce nitrogen dioxide, water, and that energy. So the forward reaction is exothermic. Now I know the previous one was, a forward reaction was endothermic, but that's because the energy term was on the left-hand side. Now the energy term has switched to the other side of the arrows, the other side of the equation, and so it switches the roles. Now the forward reaction is the exothermic. Energy is exiting the reaction. That's a reaction which is favored by a drop in temperature, and so we see equilibrium moving to the right again. So we'll use up the N2H4 and the oxygen and produce more of the nitrogen dioxide and water. Ultimately, what Le Chatelier is telling us is ways that we can manipulate a reaction to produce the products we want. So if the reaction wasn't producing enough nitrogen dioxide or water, we could lower temperature and trick the system into compensating for that loss and moving equilibrium to the right. Next one, decreasing temperature again, we're losing energy. But again, look how that energy term, the 31.38 thousand calories, has hopped across to the left-hand side. So we switch the roles of each reaction from exothermic to endothermic. We know that a drop in temperature favors the exothermic because dropping temperature means we've lost energy, and we can replace it by favoring the reaction that produces energy. But now we have to read the equation from the right to the left to see that energy coming out. So as temperature drops, we'll use up more carbon monoxide and hydrogen and turn it into more carbon and water and more energy. So the system is always finding ways to compensate for the change that's being forced on it. Equilibrium will move to the left, favoring that exothermic reaction. Next one, we are back to increasing temperature once more. Reaction with phosphorus trichloride combining with chlorine to produce phosphorus Penta chloride and giving out energy. So increasing temperature, we now have too much energy. If we have too much energy, we have to use it up. We need to favor a reaction which uses up energy. That's the endothermic reaction. And so as we look at the equation from right to left, that's the reaction. That's the path where energy is being consumed. We start with the phosphorus pentachloride and the 26.5 thousand calories each time. and use them up to produce phosphorus, trichloride, and chlorine. So if the temperature is too high, favoring the back reaction, the endothermic reaction, will compensate for the temperature being too high because we'll use up that energy. So be careful with temperature changes. It's very easy for it to become dizzy. This is one of the things that makes chapter 6 tough. First off, remember, get your interpretation of the reaction correct. Exothermic reactions show the energy like a product. Endothermic reactions show the energy like a starting reactant. And then when we talk about those temperature changes, an increase in temperature favors the endothermic, and a decrease in temperature favors the exothermic. Okay, we have a crisis. My daughter show has paused on Netflix. Why does it do that so quickly? Right, that's probably an opportune time. Let's take a 5-minute break. Look at the example questions of 6.5. Try and work out your answers, and we'll go over them. And I think we'll probably call time there, and we'll leave pressure to Friday, so we're not giving ourselves too much to do today. Back in a sec. Uh-oh. It's switched off. Would you like to? Yeah? No? Right. What's the final answer? Yeah. All right, we're back. So I did get another makeup assignment produced this morning. It's on Lewis structures. That's available for people who've had to spend some time quarantined and missed labs. So you can watch, you can use that for one of the missed labs. Let's see. So we had some equations to look at, or some questions to look at. So ammonia, consuming heat energy to produce nitrogen and hydrogen gas. And so our first question is, what is the effect of adding ammonia, NH3, to the reaction? So of course we said that for adding a chemical like ammonia, our mantra is that we've now got too much of that chemical. And so to compensate, the system is going to use that chemical up. Again, apologies for my terrible handwriting. It's just my ultimate shame. So to use up that chemical, we're going to look at an equation. There's the ammonia there. And we're going to move away from the chemical position. That's a movement from left to right. That movement from left to right is favoring the forward reaction. So we can say that the forward reaction is favored. So we'll use up the ammonia because we've got too much when more was added, and we'll produce more nitrogen and hydrogen gas. Any questions about that one? Doing okay? Second question, what would be the effect of adding a catalyst? So we had talked about adding a catalyst. If we draw a quick energy diagram, improvise something anyway. So the heat term is on the left, so the forward reaction consumes heat. The forward reaction must be the endothermic reaction. So we get an energy diagram that looks a bit like that. There's more energy going in and less energy coming out for the forward reaction. And so the catalyst lowers the energy of activation. But if we follow that dotted line, or the catalyst effect, it's not just lowering the energy of activation for the forward reaction, it also lowers the energy of activation for the back reaction as well. So lowering the energy of activation, EA, but it does so for both reactions. So neither reaction gets the upper hand. Equilibrium is unchanged by the addition of a catalyst. Adding a catalyst does not affect the position of equilibrium because we gave a boost with easier collisions for both the forward and back reaction. The only notable difference is that we actually reach that point of equilibrium faster. So instead of taking maybe an hour for equilibrium to be established, it will take considerably less than an hour, maybe just 10 or 15 minutes. But the amount of each chemical is unchanged because the position of equilibrium is unchanged by adding a catalyst. You cannot force the system to make more of the chemical you want by adding a catalyst. Let's see, next one. And so next one is, what would be the effect of removing hydrogen? So now we're removing a chemical, and so we don't have enough of that chemical. And so the system has to compensate when a chemical is removed by making more. This is what Chatelier's principle is telling us how the system compensates for the disturbance. So when hydrogen is physically removed, the system needs to make more hydrogen to cope. So we said our mantra for removing chemical was, and there's our hydrogen there, when a chemical is removed, we move towards the chemical, using up ammonia to produce more nitrogen and hydrogen. That's how we compensate. That's a movement from left to right. We're favouring the forward reaction once more. When a chemical is removed, move equilibrium towards that chemical. And you can see from that movement, left to right is the forward reaction, which is actually being favoured. Just out of curiosity, if you were holding that test tube when the hydrogen was removed, what would happen to the temperature of the test tube? Would it feel hot or cold? Any thoughts? Look where equilibrium is heading. We take this stuff and turn it into this stuff every time the forward reaction is favoured. So to realise if it's going to feel hot or cold, is that movement from left to right, is it consuming energy or is it producing energy? Right, okay, so on the message board, our shy members are telling me, yep, if you move from left to right, you're consuming that energy, and so there's going to be less energy in the reaction. It's going to feel cold whenever the forward reaction is favoured. Good. Let me clear up around my equation. Let's see what we've got next. Decreasing temperature. Goody goody. A question about today's chemistry. So what would be the effect of decreasing temperature? So we decrease temperature. The reaction is losing energy. And if the system is going to compensate, we need to replace that energy that's lost. That's the system's response. Temperature is dropped. We turn down the heating on the hot plate, and the response of the system is to try and replace that energy. Now, the reaction which replaces energy is the exothermic reaction. Energy exits an exothermic reaction. And so, whoops. Everybody still hear me? I just got a random beep on my computer again, but it looks like my headset headset is still on. So I don't know what that was for. So we look for the exothermic reaction. That reaction is giving out energy. So we want the energy term to look like a product coming out of the reaction. And so that would be a movement from right to left. We consume these chemicals, we produce these chemicals and produce energy. And so that drop in temperature, which favors an exothermic, is going to favor the back reaction. Because the back reaction is giving out energy along with the ammonia, NH3, the back reaction is exothermic. We favor the exothermic when temperature drops we favour the endothermic when temperature rises, because the system is trying to compensate in each case. Okay. One last one, question on the equilibrium constant itself. So I'm going to have to clear up all this text and move on. Let me just create some space here so I can keep the equation on the page. Right, so still see the equation. So it says if equilibrium concentrations of our chemicals were 0.8 for the ammonia, 12 for the nitrogen, and 3 for the hydrogen, calculate the equilibrium constant and predict where the position of equilibrium would be. So let's see, what color will I choose this time? Important decisions. Let's go with purple. So for calculating the equilibrium constant, remember, it's the products of the forward reaction divided by the reactants of the forward reaction. So our products are nitrogen and hydrogen. So nitrogen multiplied by the hydrogen. Hydrogen has 3 moles in the equation, so we take it to the power of 3 divided by the ammonia, NH3, which is taken to the power of 2 because there's 2 moles in the equation. We don't include the energy because that's not a chemical and we can't measure a concentration for it. And of course, we check to see if there are any solids, which would be the other thing we take out of the equilibrium expression. And of course, water when it's paired with aqueous conditions for one of the chemicals in the reaction. So we don't have any solids. We don't have water when there's aqueous conditions. And so we're fine. Nothing else to be changed. We just have to start plugging in values. So for the nitrogen, that was given as a concentration of 12 molarity, 12 moles per liter. The hydrogen is given as 3, but that's to the power of 3, divided by the concentration of the ammonia, which is just 0.8. But that's to the power of 2. So simplifying that, let's see, 3 to the power of 3, 3 times 3 is 9, 3 times 9 is 27. So 27 times 12, oof, 10 would be 270. Let's see, I need to get my calculator up. There she is. Give me my calculator, it's hiding behind it. Let's see. Nope. Another strange ghostly beep. Okay, where was that? So 27 times 12, 324 for the top half, divided by the 0.8 to the power of 2, so 0.8 times 0.8, which will give us 0.064. And so we can clearly see that we've got mostly products, because it's products divided by reactants, 324 compared to just 0.064. And that therefore gives us a value of 5062.5, the equilibrium constant. So our K value, whoops, that got away from me there. K value is greater than 1. And we only get that when we've got mostly products of the forward reaction. So we can say that the forward reaction, if its products are so plentiful, has been doing a good job. And so we can say that the forward reaction is favored by equilibrium currently. Okay, any questions about that one? Doing good? Silence. Okay, I guess I'm not hearing any questions. Must be, and it's tricky, definitely tricky. Remember, get this into your head. Recognize whether an equation is telling you it's exothermic or endothermic. If that energy term looks like a product, it's an exothermic reaction. If the energy term looks like a starting reactant, it's an endothermic. Then remember that a rise in temperature favors the endothermic, a drop in temperature favors the endothermic. Okay, that very nicely actually takes us up to time, so we weren't going to get onto pressure anyway. And so that's going to be our last subject for Friday, along with a couple of extra practice questions. I'll put a new Chem Talk video up today, probably put up the temperature one, as soon as we've been talking about it, and put up an extra couple of questions of the day videos. And we're still over a week away from the test, and we've just about covered all the material. We should have been thinking about Chapter 6 during this past week, in between doing some studying for the Chapter 5 exam. Okay, guys, thanks for joining me this morning. I'll see everybody on campus on Friday. Stay safe, wash your hands, wear that mask properly. Nope, everybody left before I could stop the video. That was quick.